Hello everybody and welcome to our KiCad tool training part 1 out of 2. In this part we are covering the topics of KiCad workflow and schematic editor. As mentioned earlier, this KiCad training is based on KiCad version 8.0. Before I explain you what we are going to do in this KiCad training, I want to show you the circuit on which this training is based. The example circuit is this NE555 timer circuit. What's the purpose of the circuit? This is the NE555 timer, and the purpose is that the red LED number 2, is going to start to blinking once you powered it up with 9 volts. This is a circuit. We are first entering into the schematic editor and then doing the layout with the PCB layout editor in KiCad. We're not going to discuss the functionality of the circuit. For this I would refer to a web page of the NE555 timer where different circuits and the internal functionality of this timer is explained. Good. Agenda for this KiCad training part 1. First I will show you where you can download the installation files for KiCad and where you get further resources for this KiCad training. Then I will explain the KiCad workflow, and finally how to enter a schematic in the schematic editor. Installation of KiCad and used resources. In order to install KiCad, please go to the web page and download the appropriated installation file. The resources for this training is mainly the Getting Started in KiCad documentation, also available on the KiCad web page for version 8.0. and I downloaded it in March 2024. If you need further information or you're interested in further videos to have also a different explanation of KiCad, I found the DigiKey videos very useful, so go to the DigiKey website and check for the KiCad training videos. If you are a student of our university of the International Master Program and following the the pre-classes for the spring term, then we will provide you additional resources in Moodle, our online platform for learning, mainly the KiCad training_year zip file, where you have a folder structure for your complete project, so this covering PCB, software, project organization, documentation. So this is already the project structure which we will use later in the spring term. And we will provide you a KiCad cheat sheets with some shortcuts for the layout editor or the schematic editor. As mentioned before, we are not going to go into detail of the functionality of the NE555 timer. If you want to get some information about this device, please go to this website and check out the internal functionality and also what other circuits can be built out of this timer. Good. Coming to the KiCad workflow. The KiCad workflow is in principle shown on the left side. First, you enter your schematic with the schematic editor. Thereby, of course, you use the symbols and library provided by KiCad. Then you have a logical representation of your schematic or of your circuit. When you want to go to the physical visualization, you have to add information about which devices you're going to use. Because, for example, an operation amplifier can be delivered as a through-hole technology device or as an SMD device. So once you have entered the complete circuit diagram in the schematic editor, you add the information about which footprints your devices are using. And once this information is completed, you can start the layouting process with the PCB editor, where now these logical connections in the schematic editor are drawn as traces, as copper traces on your PCB. Once this is finished, you have your representation of your PCB in your PCB program, and you see the different copper layers where you have connections between the different layers and where you have drawn the traces for your signals or for your power planes, for example. If you go to production, the interface for the manufacturer are the so-called Gerber files and drill files. So the production of a PCB is mainly a mechanical chemical process. So the Gerber files are only representing the geometrical dimensions of your copper planes and copper traces, and in the drill files where are drill holes between the different layers, or if they go through a complete copper stack. So the manufacturer only takes these mechanical dimensions of the copper planes and drill files, and based on this produces your PCB. Of course, he's going to check if the Gerber files are complete and correct, but only in terms of producibility in a mechanical sense. He's not going to check anymore if it's electronically functional circuit, or if it's electronically doing the function you intended by designing this PCB. So that's why once you have finished your PCB, you export the Gerber files. You use the Gerber viewer to compare manually this Gerber files, or the Gerber files view of your PCB, with the PCB editor view. In order this is the same, and you have to ensure this electrical connections are proper. Then you will send the Gerber files and the drill files to the manufacturer, and after some days or weeks you will come back. You will be your nicely designed PCBs will be sent to you back from the manufacturer. If you now look in the upper part, Schematic Editor, PCB Editor, you see that you have here backward annotations and forward annotations, these dotted arrows, and they are representing that this process from schematic to PCB is not linear, but it's an iterative one. Why is it iterative? For instance, for example, you start your schematic, you entered your schematic, you start the layouting, and during the layout process your colleague comes, oh, in this part of the circuit we cannot use the 1/4 watt resistor, we need a 1 watt resistor because the losses are higher. And then this means normally that the physical dimension of this resistor increases and the footprint changes. So during the layout process, the footprint changes. And this is done with the forward annotation. You change in the schematic the footprint, and then you say update my PCB, and you can change still use the so far layouted PCB, but one footprint changes. And the same is when you design your layout and you say, oh, I want to change the device and I need another footprint, then maybe the pin numbering is changing, and then you have to update your schematic. So this means with the dashed arrows, this is a more or less iterative process. Good, coming now to the KiCad Project Manager. This is the window which pops up when you start your KiCad program. On the left side, you see the KiCad folder. So for us, it's the NE555 timer. You see here the folder which is realized, the NE555 timer folder. And in this folder, you see in the beginning 3 files, the NE555 timer.KiCad project file, the PCB file, and the schematic file. And I want to point out at this point that KiCad is KiCad organizes the projects in the folder. So this means when you only take out the schematic or PCB file and you change it and you put it back, then the data is not linked anymore. As I said before, we have this iterative process between schematic and PCB. So please always copy the complete folder if you want to share or want to change something, and don't only copy simple solely some files, because then you will get corrupted data. Good. The schematic tools, or the tools which are provided, are shown here on the right side, and the design process here, or the steps, are going here from top to bottom as before. You start with the schematic editor, you use the PCB editor, and you check your PCB with the Gerber viewer before you send the Gerber files and drill files to the manufacturer. Additionally, KiCad provides a symbol editor and a footprint editor. If you need to make your own symbols or own footprints, which might be the case if you have certain devices which are not provided in the KiCad library, or you couldn't download this information from the vendor's webpage. And you have some further tools helping you, for example, calculating resistance or capacitance of traces, etc., which is sometimes important if you have high-speed signals. Now let's talk about how to enter the schematic into KiCad. In order to do so, we have to do the following steps. First, how to read and draw a schematic. I will talk about the agreements, how you have to draw a schematic that other persons can read it. Second step, draw a schematic in Schematic Editor. Here we'll show you how you add the symbols in the Schematic Editor and wire them up. Third step, we will perform an electrical rule check, ERC check. Here we check if KiCad has all information needed to go to the next step, the PCB layouting. Fourth step is we are talking about not connected pins and what to do with them and why we need power flags in the schematic. Fifth step, we will assign footprints to our symbols. And in the sixth step, we will generate the bill of materials, the so-called BOM list for your PCB. I will explain how to read a schematic in our example timer circuit. In general, you read a circuit diagram from the left to the right in terms of the signal flow. And in the center, you have your active device or your main device. In our case, the input to activate our main device is somehow the release reset by putting the reset pin to +9 volts, leading to a charging and discharging of capacitor C2, and this is leading to a blinking LED 2 at the output on the right side of your circuitry. At the input side, we have always or sometimes also some circuits concerning about the power supply. In this case, we have a green LED indicating the power supply is connected and a capacitor C1 to stabilize your power supply. In terms of power supply, at the top side is normally the positive power supply, in the middle would be ground, and at the bottom would be the negative power supply. In our case, we have only a positive power supply towards ground, so at the top is our positive power supply, and at the bottom our ground plane or ground line. Now, in order to enter the schematic into your KiCad program, my engineering best practice is to print out your circuit diagram you want to enter, put it in front of your keyboard in your computer, and you draw it into KiCad. And if you have some questions, annotations or notes, you can just use your pen and put it onto your printout. Well, if you open up KiCad and you started your schematic editor, this window will pop up. On the left side, you have some icons for the display settings. At the top side, you have general icons like zoom in, zoom out, or later on perform the ERC check. And on the right side, you have all icons you need to enter and edit your schematic. The first thing you should do when you open up such a schematic, you have to fill out the page settings. This is in the lower right corner. And enter the date, project name, version number, and authors. In our case, the authors are going to be the lab group you are assigned to. So this is going to be A, B, C, D, E, F, G, or so on. And all student numbers which are in this lab group. Later on, this information is also put on the silk layer on your PCB. The silk layer is the annotation layer, where you can make annotations about your PCB on the coating of your PCB. And like this, we can assign to your group the correct PCB later on. How to enter this, we will see quickly in live demo of KiCad, but you can double click either on the page settings area, or you click here on the page setting icons, or you go via file and preferences settings. Once again, some words about how to read and draw a schematic. We talked about from left to right, input to output. Top side is positive supply, bottom side is negative supply. We can say in our schematic we use the upper right, or better the upper left corner. This is this area for the power supply. We use the center for the circuit performing the task, so we put the NE55 timer in the center of the schematic. And we make annotations for routing into the schematic directly where you have to pay attention. So if, for example, you have a signal here which is prone to interferences, then you put here directly a text prone to interference, and the layouter who's layouting your circuit based on your schematic knows already at which signal he has to pay attention. The text must be readable, so you write the text in landscape, or you turn your schematic 90 degrees positively, mathematically positive, so this is counterclockwise, and you write your annotations. Don't put annotations in all kind of orientations in your schematic. This makes it a little bit messy and hard to read. The last thing I want to mention by organizing your schematic is that you have here different quadrants or sectors. The rows are labeled with A, B, Z, D, and the columns are labeled with numbers 1, 2, 3, 4, 5, 6, and so on. So for instance, we can say, for example, in the quadrant or the area A1, we put our power supply circuitry, and in our area B23, we put our NE55 timer circuitry. Like this, you can organize a little bit your schematic. Additionally, if you write a documentation in your schematic, you can use this information to reference to different areas in your schematic or different building blocks in your schematic. Now it's time to start KiCad and fill out the page settings and start to place the first components. Now, to start, we start our KiCad program. The KiCad project manager appears, and we have to define a new project. So file, new project, file name, NE555 timer, and the project manager automatically generates the schematic file, PCB file, project file. And since we start to enter the schematic, we click on the schematic editor. Now the empty schematic appears, and as we said, our first step is to enter the project information, so the page settings. For this, we click here on the settings for the page size and block information. Here we can set different parameters for the paper, for the view, and so on. What's important for us is the title block section. We take the date from to date. We take as a revision 0.1, since we are under construction, no release. I take the 1 for the first release version. As a title, we take NE555 timer blinking LED, company, University of Applied Science Darmstadt, and we take author as .1. So this is the information we discussed in our PowerPoint presentation. We click on OK. This information is automatically inserted in the lower right corner. We zoom in, we see exactly this information. Now the next step is to insert our components. If you click here to fit to zoom, you see the complete schematic again. Now we are ready to place our components. In order to get into a schematic editing, I first want to explain how to zoom and move the canvas. Scrolling and zooming is the mouse wheel to zoom in and zoom out. Scroll vertically, Shift plus the mouse wheel. Scroll horizontal, Control plus the mouse wheel. If you want to move the canvas, you have to right click, hold and move, or click the middle mouse button and move. Now we perform the following working steps. First, we place all components we need into our schematic. For the supply voltage, we use the area A1, A2, the quadrants. So this is going to be here in the schematic, A1 and 2. The design circuit, so our NE55 timer and stuff, B1, C3. So this is B, this is 3, B1 is here, C3 is here. So it's going to be in this area where we put our NE555 timer. To add a device, you have different possibilities. The shortcut is press A, or you select the device selection or adding icon on the right side of your window. Then we place the connectors. The connector is just the symbols for connectors in order to supply the supply power. Also the connectors we find at the device libraries. Then we add the component values, so giving the resistance values and maybe inductance values, etc. When we are finished, we place the power and ground symbols. For this, we can directly click on this power icon. Here on the right again, here, the power icon. Or we push again generally the A for add a component. When they are all placed nicely in order to wire them up, we wire them up. You can push the W for wiring, or you hit the wiring symbol, this line on the right side of your window, to wire up. And if you have wired out up, some nets we will associate with some names. You can L for label, or you go on the icons on the right side to this A with the underline to put them labels on the nets. Now let's do this with KiCad. Now we start to place all our components. So we go to Add Component. The symbol library is loading. And we start through our NE555 timer diagram from left to right. We'll start with power supply. We need a resistor. For this we can go to the search field and put R. And we get a resistor from the generic devices symbol, so device, generic symbol for common devices. And here we have only the symbol, and we see it's no footprint assigned yet. So we take OK. Since we have this power supply, we want to put it in A1, A2. We zoom in here a bit. A1 and 2, power supply symbol. LED, the resistor, we add the light emitting diode, search field LED, then we again from the generic device library take the LED, adding it. If you push the R for rotate, you can rotate the device. So we have these two devices. Then we need a capacitor. Again, we add a device. We put C. Again, generic symbols for common devices. Unpolarized capacitor, that's correct. And we put it here, and so we have our components for our supply connection. If we want to deselect, at the moment we still can add components, as you see on the cursor how it's moving. We press escape. Now you can mark them with the left click, and you have all marked them together. You put an M for move, and we can move these devices to A2. Since later on we will have a connector which I would like to place on A1 quadrant. So that's for the supply voltages. Now we add devices for our NE555 timer. So we put as first the AA555 timer, we put A, and then you can also search here for this device NE555, and then you get here under the timer assorted devices, and you see this is all the same device and different manufacturers, and mostly important, different packages. So you see here now on the right the symbol for our schematic, and at the bottom the footprint associated with this symbol in this case. So we see here SOIC package, but we want a PDIP, plastic dual inline package, where we have this, which is through-hole technology and it's not surface-mounted devices. You will see how the footprint changes. And on the left side we get some further information. NE555P for plastic package, keyword single timer 555, reference. Then we see which footprint is associated at the moment. DIP 8 width, it means DIP dual inline package with 8 pins, and the width is 7.62 millimeters. You can also now click on the data sheet, and the data sheet will open. So that's quite handy at this program. But for the moment it's sufficient for us. We take the PDIP device and select it and place it in the middle. B1, C3, so B3, this is this area, so more or less in the middle. It's going to be here. Good. Then we zoom in a bit to place the resistors we need. So here we see that we need a resistor bridge with a capacitor. So we put again our device. Search for R. Recently used. It's also good. So we need 2 in a line. And then we need a capacitor, this time polarized. So here we have to go to device. In this case we try it this way. We go to the generic devices, interfaces and stuff. We need the search field, and then we will see that here comes groupings, and then somewhere we have this device, and then we see unpolarized capacitor. In this case is C polarized. You see this device, also now footprint specified. Okay, it's going to be connected here. Then we need a light emitting diode again and the resistor. Add. Rotate with R. Somehow at the Q pin is the output, so we put it here, and we put the resistor down here. So now we have placed all components which we need, and now we have to place the connector. So this is here to have the off-board connection of our power supply. Also we take adding symbol, and for the connectors you have the connector section. And we need just a single generic connector, but not 1 by 1. We need 1 by 2. It's looking like this. It looks fine. Passive device connector 0102. And later on we can select a footprint which is suitable for our design. So we put these connectors here. Well, now we have placed the connectors. Now we should add the component values. So for this power supply indicating LED, we have no component values given, so this is you have to calculate on your own. Then for the stabilizing capacitor, we have 100 nanofarads. So you hover over the symbol, right click, the property menu opens up, and you can edit the properties. And then you have see here reference C1 is our device. And we can put a value 100 nano. Okay, now we go to our main circuit. R2, 50 kilo ohms, 50K, and polarized capacitor. 1 second, doesn't work. Edit. What is? The footprint. Of course, this was the wrong line here. 15K. Okay, and you see here 15K. So you continue this until you have added all values. For the LEDs, we can assign the property name value LED. Yes, you can put this is red, correct? Red, and up there we take as the value LED green. Now we have to do step number 4, place the power and ground symbols. So what does it mean to place the power and ground symbols? If we have a look again at our circuit, we see that here we have connected all devices which needs the positive power supply with a wire to the top side of our schematic, and if we need ground on the bottom side of our schematic to one wire. And the same, if we now think about our schematic here, if we want to connect all devices with the power lines, let's say from pin 2 to the anode, to the capacitor, to the NE555 timer, it gets a little bit messy, and you don't gain any further information because the power supply has to be somehow connected to your device. That's why at bigger schematics we don't draw the power supply lines anymore, but we use the technique connecting by name. What does it mean? This means we put here some symbols or a wire, and we label it, for example, VCC for the positive power supply, and then we connect here also a wire, name it VCC, and then these two wires are connected. So later on in the PCB layouting program, the layout program knows that we have to make a trace from this device to this device, but in the schematic it's not shown, it's here connected by name. And this is typically done in greater schematics or bigger schematics for the power and ground traces. So that's what we are going to do here too. And we start at the power connectors here at the upper left corner. We connect first our power supply, so we go to add power symbols and we select VCC for the positive power supply, this one, and we rotate it. It's connected here, we connect it here to the power indicating LED, connecting it here to our stabilizing capacitor, and we go down, we have to connect it to our VCC of our NE555 timer. We connect it to the charging and discharging circuit, and we connect it. That's all. Correct? Yes. Now we have to draw the wires. This we go to select wire. Always one click only. Left click. Zoom out. Zoom in. That's it. And that's what's very handy in KiCad now, of course, is you can now select here highlighting net on the right, this is this symbol. So you connect, for example, on this net, and all VCC or VDC lines are now connected. You see, all VDC are now connected together. And this means connecting by name. So we do now the same for the ground. Again, power symbols. We go up to ground. You see here we have all the choice between different grounds. Ground analog, ground digital, general ground. We just take ground in our case. First we have to connect here to the power connecting pin. With R you rotate your device R, W you wire. Then we add a power ground pin again. Selecting it here, positioning it here. Move there. This one is a little bit lower. To put it nicely, should be on one vertical line, horizontal line. Sorry. You click on the device and then you can just move it up if you release it correctly. You wire them now. Remember, if you just hover over it and you put W, you automatically start the wiring, right? So as you can see, I didn't hit the point, so we didn't connect. We hover over the connect pin, W, it's connected, and ending here with the live click once. So there's ground pins here. We will do the same for the NE555 timer circuitry. One ground pin here. And we check again if they're on the same height. So we move it's a little bit, sorry, it's a little bit down, let's say to here. Should be in one line. So okay, and now we also wire up this power the connecting service W, hovering over the pin, connected, left click, W, connected, left click, W, connected, left click. Okay, now let's have a quick overview and zoom to fit. We have connected our ground pins and our VDC pins. Now we can start with step number 5, wire all up. We start again at our power supply entrance circuitry. So this is everything is done, I think. Connecting power pins. I put one always to ground and two at VDC. VDC connected correctly and ground connected correctly. So for the power pins, power supply, we are fine. Now let's go to our NE555 timer. And here we have, of course, to do some work. We start with the trigger, TR point, which must be connected to the threshold. You hover over 2, push W, it's connected. Now we make a little bit of curve and go to threshold. And then we see that we have to connect the reset to VCC. Again, we take here our VCC symbol and we don't draw a line. We took VDC, right? So we take VDC, re-rotate it, place it, W, hover over it, W, connected, left click, connected, and finished. Good, the VDC. Then we come to the charging and discharging circuit with this one, and we see that discharge has been connected to the upper part of R3 and threshold to the lower part of R3. So in order to look it nicely, we connect here W, left click, here went something wrong, W and left click, and then we can connect here W, left click, and we have this connection here and here. So this looks quite nice. If you want now connect the output, it's going to pin 3, diet, so on. So this is the connection we have done. I hit escape to release, and now we make it this circuit a little bit nicer. So R3 in the middle of these 2 points. So we click on R3 and then we click and hold, and so we can move R3 while the connection is remained, you see. So a little bit more in the middle, looks nicer. And here we can move R3 in the height of this capacitor and the diode of the height of R3. So to make it a little bit tidying up your schematic is never bad, because if you want to understand the schematic, it's good if it's tidily drawn. Now we save this, and we have entered our schematic, I think. Check again to our circuit we want to enter. We see, okay, this part we have done at the power supply. We see our NE5 timer, trigger to threshold, ground supply. We see our R3 to VDC, going to R3, polarized capacitor, but I think we forget this diode here in parallel to R3. Yeah. I just moved this a little bit to the left, and we compare again. The output is connected to the light emitting diode and then to the resistor R4. So that's fine, but what's missing is this diode, but it's not a big problem. I think it's 1N4148. So we go to add a device. And now you can either just put a diode. Try this, D for diode, go the generic diode. And we can try if you find one N4148. So it's also seen as a diode, and he delivers us already the corresponding footprint. So we can take this one and we rotate it correctly in this way. The same vertical position, then R3, D3, push with pressing W, left click, left click, left click, left click, left click. So now we save. This looks now fine. Big picture. To sum up now, we have entered our power supply circuitry in the area A1, A2, and we have drawn our main circuit with the COI device, the NE5 timer, in B1 to C3. What we now can do to finish our entering the schematic, we can label some nets. So for example, we can label the output net. How do we do this? Zoom a little bit in. This is going to be our output net, right? So we go here to label net. Label net window pops up, and we call this output. Adding it here. Good. And the last thing I want to show you is to write some text for annotations. For example, it might be useful to keep here this line from threshold to trigger as short as possible. So we take here draw a text item, and then we say connection tr as short as possible. So we can say, okay, default font, that's fine. Make it bold. Let's see in the preview. We can give it a color. Let's say we take a blue. So we get it on our mouse tip, and then we can rotate it as we learned. Okay, here this is not possible. You turn away, I said, so we just put it here. And then we have our comment connecting tr to tr as short as possible. So this might be the hint from the layout guy. But I'm not really happy with the position. Do it like this. Okay, so that was the last step of our schematic entry, and we will continue with the next step theoretically on our PowerPoint. Once we seem to finish, we have to check if the pins of all symbols are really connected, or if maybe we hit, for example, here with the wire 1 pixel beneath and it's not really connected to the pin 3. In order to do this, we can do it manually. So we select the device, and now we can use grab G, press G, and then move it. This means the connections to the wires remains, and then you can see if all pins are connecting and some wires are circling around. So that's fine. For the NE555 timer, we go to R3, put G, also working, and like this, selecting the device and pressing G for grab. You can check if you really connect the device or not. Of course, I will do this with the main devices in this way, but to do it manually all the time like this, it's very to make it for the whole schematic like this, it's a little bit time consuming, and there's an automatically electrical rule check which we are going to perform now. So we click on this symbol on the top side of our window, perform electrical rule check. The electrical rule check window pops up. We see violations, show all, nothing exclusions, no exclusions, so errors and warnings, and then we run electrical rule check and we got 4 errors. So let's go. Input power pin not driven with output power pin. If you mark this error, your cursor jumps to the position, you see. Yeah, it's going to be this position is the pin not connected. Then this is input power pin not driven by an output power pin. Here, input power pin not driven by any output power pin. Input power pin not driven by an output power pin. So these are the few errors, and to deal with them, we go back to our PowerPoint presentation and I explain it. But that's very handy. You can click on the error and it goes to the error where it occurs. The errors are also marked with this red errors. Now let's talk about the electrical rule errors the electrical rule checker encounters. Let's talk about the first error, the input power pin not driven by any output power pin. So what KiCad is doing, if you correctly connect devices to each other, it's that, for example, the VCC, here it's the input power pin, should be connected to another device which provides an output power pin. The problem here is that VDC is not connected to another device, but connected to a connector. And the connector doesn't have any output driving port. So because it's an off PCB supply. To mark this, we have to add here a so-called power flag, which is just a symbol we use in the schematic, and then it's marked that this pin is driven outside of the board, and then we don't get errors anymore for VDC, and the same holds for the ground error here. So now we understand the problem with the input or input power pin not driven by any output power pin. Another problem we encountered was pin not connected. This is in our U1. This is our NE555 timer. Pin 5 CV input line is just not connected. And if it's intentionally not connected, you should mark it with a not connected symbol. Otherwise, for KiCad, that's also an error, or it will remind you that you have a pin which is not connected yet. To resolve these two issues, we use the ERC result, and everywhere we get pin not connected, we put this not connected symbol there. For example, we put it here. And at points where we have this power pins are not driven, we put this power flag. We can find it again over our power symbol icon, or we go to add a device, power, and then find our power flag, and we add the power flag 1 at VDC and 1 at ground, and our errors should be gone. Now we have seen the errors from the electronic root checks, and we start with the input power trim not driven with any output power pin. We zoom a little bit in, and you see if you click on the error, automatically goes to the pin where this error occurs. So input power pin not driven by any output power pin. As said, we are going to try to fix this with a power flag. So we go to add power symbols, and then we write power flag, and it's already coming, power flag. Connect this one to ground and the other to VDD. Rotate with R, adding, and fine. This should be fine now. We can move a little bit. We can also rotate this. Yeah, so that we have a little bit nice overview. And then we connect. Oh, let's just run the ERC again to see if the power flag errors are now gone. The input power, the driven by any output power pins, so the should be gone. Okay, and now only error input power pin or pin not connected is left. We check. See. So we will place here the not connected symbol here, draw no connecting flag, the ERC, and save. And now we run the ERC again. And normally it should be now error free. So no errors anymore. Very nice. You see that, for example, we can also have a tab here for ignore tests, and edit ignore tests, and you can ignore tests. Pin not connected, for example. I don't recommend this because you should have really an error-free schematic before you proceed with the PCB layouting. If you ignore some errors, you really have to know, or you should be aware what you are doing. So in the first step, when you're a beginner, don't use this option to ignore any errors. Okay, so let's see what we do next. Now our schematic is finished and we have all the connections. Now let's see what's the next step. Since we have now an ERC-free schematic entered into KiCad, we can now perform the last two steps: footprint assignment and generating the build of material. In order to assign the footprints, the footprint assignment editor is popping up. In the middle are the symbols where you have to assign the footprints. On the left you can choose one of the footprint libraries, and on the right you can choose one footprint out of the selected library. I will show you how you select the correct footprint, obviously between surface-mounted devices and through-hole technology, but also to check some parameters like horizontal, vertical assembling, or length, diameter and pitch, and what this parameter means in your concrete PCB design. Once this is done, we can generate the BOM. For this you have this window where you can select different possibilities how this BOM is generated. For instance, I like to have as a reference the group by name, since then I know how many capacitors do I have, and maybe I can select how many capacitors of the value 15K I have, etc. Further, I want to note this is the automatically generated BOM list based on the components you have to place on your PCB. But the generic BOM list build of material also covers the distant bolts and screws you need for your PCB to mount into your case, or for example the cable for the plugs to plug in the power connectors into your PCB. So make a copy of this automatically generated BOM list from your PCB and manually add the additional assembling components and components to power up your system. Now we can assign our footprints. To do this, we start the footprint assignment tool. In the middle we find the symbols and the footprints we have to select. We see that, for example, diode D3 1N4140A is already selected, and for the NE555 timer the footprint is also selected. Let's start with the capacitor 100 nanofarads. This is a non-polarized capacitor. So we take here the capacitor THT through technology, and then we know 100 nanofarad. That might be a resistor from the type FKP2. So we make a pre-selection, and then you have to see what component you have ordered or you will order, or which you have foreseen for your circuit. And then you see here the length, the width and the pitch of this capacitor. So a pitch of 5 mm is fine, a width of 3 mm is fine, and a height of 2.7 is also suitable, so you can say that's pretty fine. If you right click, you can have a view on the selected footprint. You see it here. You can also use now measurements to measure here the pitch 5 mm between the two connectors. And you can also say get an overview how it's looking 3D. Then you click on the show 3D viewer, and then you get also an image on ID of your component, how it's looking if you later assemble it. Good. So for this capacitor we take this one. Then we have to select the polarized capacitor Z2. You see this is the big one for discharging and charging. Of course it's also THT capacitor. So we go here, check capacitor, and somewhere, yeah, it's already CP. Polarized, and then you see for the polarized capacitor, it's an electrolytic capacitor. It's mainly radial, so you have it given a diameter, for example, diameter of 10 cm. So this means the diameter of your capacitor is 10 cm, and the pin pitch, so the connectors have again a pitch of 2.5 mm. We can view the selected footprint. You see here the pitch again from 2.5 mm from here to here exactly, and we see the diameter from here to here going to be roughly 10 mm. Depending if you take the guard rings and stuff, it's a little bit more because of the placement on the PCB and tolerances, but the 10 millimeter diameter capacitor. So this is reasonable. You can have a 3D view on it. Yeah, these are the typical electrolytical capacitors where you mark the negative connection, or where you have to put the negative potential and where you have to connect the positive potential. Good. So we select this for our polarized capacitor. Then we have to select the LEDs. So we can go here and search for LED, THT. I think we take the 5 millimeter diameters. Then we see here 5 millimeter clear RGB, and we take just 5 millimeter. We have some. We take the 5 millimeter. If you select the footprint, this looks not bad, right? And the color is red, but it's fine. This is what we select here for the LEDs. LED green. We have LED red. And we are fine. And then we have the connector to select. You go here, connector. Now you have a whole bunch of different connectors. We take here are the different high rows, different manufacturers, Dean, etc., etc. If you take the standard connector, we know we want to have the pin headers exactly, and we take a pitch of 2.54 millimeters as a standard pitch. So you have a lot of components which you can order and select, and then you can use here pin header 1 by 1, horizontal or vertical. We take 1 by 2 because we take 2 pins, and we take vertical. So these are the 2 pins. Pin 1 is marked, and if you look at the 3D viewer, it's going to be this pin header, which is easy and often used for simple builds. That's fine for our connector. Then we come to the resistors. This one we haven't calculated yet, that's why we have an R, but these 3 resistors are calculated. If we go back to resistors, resistors THT. Then you have here the German industrial DIN. This is how they are manufactured, and what's the package type. Very typical is the 0207 with a length of 6.3 and a pitch of 2.54 vertical, or the resistor standing vertical. That's not so interesting, but the one where the resistor is horizontal layout on the PCB is the most common, so we take this one. Let's have a look at the footprint. Looks fine. 3D view, yeah, that's what we want to have. We can use here the small pitch, which is very tightly bent at the package. Maybe we find someone with a greater pitch. So this is this one, you see. Just the next one, the same length, same diameter, but the pitch is greater. Let's have a look. Yeah, you see here, now the banding is not so tight at the package. We assume, yeah, and this is seen here. There's a little bit more distance, make it easier to assemble later on and doesn't stress so much the components. So we take this footprint, for instance, in this case. 1, 2, 3, and 4. Okay, you click on OK, and we have selected all footprints. And now we save. Good. So now we have assigned footprints, and now we are going to generate our bill of material. We go here to BOM, build of material. And in the beginning you see here the export view. You can choose a delimiter, string delimiter, reference delimiter, etc. Output file, format, aspect, whatever you want to take. For us important is edit. We want to group by reference. See here, perfect, polarized, non-polarized. We have to give the value here. We haven't yet given to the schematic as I see. See here. Anyway, that's fine. And then you can click on export. We have to give a file name, of course. Any 555 BOM. And it says where you wrote to the BOM. Good. So this is how we have to enter our NE555 timer circuit into KiCad. Now we went through all steps to enter a schematic into KiCad. It's up to you now to do this exercise to enter this schematic on your own into KiCad. And I want to give you for this some best practice advices in order to avoid some pitfalls. And it's also a sum up of maybe the most important points and steps from this training. First, put the schematic printout of freehand sketch in front of your keyboard. Second, fill in the project data in the worksheet info box in order not to forget it later on. Third, the aim is an ERC error-free schematic. Use the no connect and powerflex symbols to achieve these. Fourth, understand all measures and numbers in the footprint description in order not to mess up with the components you order and the components you used as a footprint. Fifth, add the mechanical parts to your BOM in order to have everything together, the cables, the screws, the distant balls, as well as the automatically generated BOM from KiCad. Sixth, order the BOM the moment you hand in your Gerber files to the manufacturer in order to have the chance to get back your boards and components to solder in the same time. I hope you enjoyed this KiCad training, and of course I want to motivate you to join the part 2 of this KiCad training covering LayoutEditor and Gerber view. Thank you very much for listening, and goodbye.